Hello and welcome to this session that is called Security Engineering from Crypto Theory to Implementation Practice. My name is Elisabeth Oswald and I work here at the University of Klagenfurt as a professor in cybersecurity. Before that, so until 2019, I was a professor for applied cryptography at the University of Bristol. And much of my current research is thanks to the generous funding of the European Union via the ERC. I have about 25 minutes with you, and what I hope you will get out of this talk is that you will have an appreciation of how absolutely crucial and important and indispensable strong cryptography is in our daily lives and for the kind of future that we can expect due to the digitalization of our world. I also hope you will get a taste of just how difficult it is to secure systems. And I want to do that by showing you some really interesting existing practical attacks that are out there. And then finally, I hope you will get some sense of our own ongoing research efforts, what I do together with my group here in Klagenfurt, in order to make implementations of cryptography, so secure implementations of cryptography, more accessible to non-crypto specialists. I want to start off by hopefully motivating you and by demonstrating to you that you, and I mean really you, should care. Because every time you pick up an electronic device and every time you interact with something online, there's really good potential that some of your data will be broadcasted to the world. Many devices that we use on a daily basis, they are connected to some other network, and we know that they regularly phone home. I'm sure you know that things like Alexa and Siri, if you use them, they will produce the data so the voice, the commands that you have used, the questions that you have asked, they will go back to the respective home companies so they can improve their service. Servers that form the backbone of our intranet structure, they are known to be used by large organizations, and we know that they will siphon off large amounts of data. If data isn't encrypted, then they will just take everything. If it is encrypted, then they will go for metadata. We also know that other servers that store databases, they get routinely hacked. I think there's been no year in the past decade where not a large company has been hacked and their entire user database has been exposed to the public. And we also know that social networks get infiltrated on a regular basis, and the data gets passed on to whoever cares, and also that users on these platforms get manipulated by targeted campaigns. You might say, oh well, these are all just conspiracy theories, so I'm hoping to prove you wrong with a few really concrete examples. So for instance, what is it actually that you can buy on the so-called dark web? Well, the dark web really these are websites that are not reachable that easily. You need to know where you're looking for, and typically they require you to use specific tools to access them. But once you've sussed this out, you're in, and it's a bit like, shopping on any other online shopping platform. There are goods, there are services that you can purchase, there are companies or providers that get liked, there are reviews being written, and prices respond to the market. An organization called Privacy Affairs, with the corresponding website name, goes about every year, traverses the dark net, kind of find out what are the best-selling items and how much do things cost. So I thought I'll pay them a visit and I'll just give you a little bit of a flavor of A, what's available, and B, how much things actually cost. So on the right-hand side of the slide, you find a table which gives you a little bit of a price comparison between the 2020 index that they produced and the 2021 index. And you can see that also COVID had an impact there and things got largely, or broadly speaking, more expensive. So, for instance, if you want to have a cloned MasterCard with PIN, then in 2020 you just paid $15 and now you pay $25, which is quite a price hike. Interestingly, the same kind of type of card, but from Visa, held its price, so maybe that's a better investment. If you want to have credit card details, then it depends a little bit on how much money is on the credit card, on the card account. So that will impact on the price, as you can see from the slides here. And obviously, the more valuable an account is, so the more money is on it, the more you pay. things that I noticed in the report were, for instance, so last year there must have been some email breach. I don't know which Austrian company got hacked, but at the moment you can buy 380,000 Austrian emails for just $10. I mean, that's really a bargain. A distributed denial of service attack, which is useful if you want to do a kind of a man in the middle somewhere, on an unprotected website, sets you back for between 15 and 1,000 US dollars, depending on the frequency of packets that you want to send to your target website. An ID card from a new member state currently costs 120 US dollars, which I think is actually cheaper than getting a legitimate Austrian ID card at the moment. A Netflix account is $44 per year, so that's nice if you want to watch US Netflix. And if you want to boost your social media stuff, Instagram 1,000 likes is just $5, so you can get very popular very easily. All these numbers are from a specific website and the URL is listed here. So please go there if you're still unsure whether this is true or not and investigate a bit yourself. But your data is probably out there already somewhere and it's being sold for quite cheap prices, to be quite honest. I've got another nice example. It's something that I quite like to also explain to my students, to just show them that because of certain decisions that were made decades ago of how certain parts of our infrastructure work, how easy it is then to carry out actually quite simple attacks. And the attack that I quite like to illustrate this is called quantum insert, and it's one of the things we learned from Ed Snowden's leaks in 2013. So the idea is the following. In TCP/IP traffic, the TCP protocol on top of the IP layer essentially makes sure that you have some form of quality of service. So if A and B are communicating on the web, and A is sending some packets over to B, then B will actually notice if these packets don't appear, because there's numbering going on, there's some handshaking going on, and so on. So TCP/IP kind of gives you quality of service. But what would happen if actually upon some form of request, say as an example, there are two responses being sent out, or two responses being recorded by an endpoint? What would happen? Well, so TCP/IP is quite clear and quite simple. Whatever arrives first is seen as the real data, and this is what's going to be interpreted and then processed. And if sort of the same response arrives again, you just chuck it away. Now, of course, if you could kind of position servers strategically in different places that respond really, really fast to web requests or whatever other requests, then you could do with that what's called a man-in-the-middle attack, because your server would intercept the traffic and respond much faster than the legitimate server. This is exactly a game that the NSA has been playing, and they called this quantum insert. And now, of course, we would all hope that the intelligence agencies, they really act to protect our interest. But in one of the revelations by Ed Snowden, what we learned was that, for instance, one of the targets for this kind of attack scenario was the Belgian telecommunications company called Belgacom. And they just wanted to know insider information about that company. And they used quantum insert under the codename Operation Socialist to target Belgacom engineers, and they succeeded beautifully. And this particular attack vector is in fact part of a larger kind of system that was developed and deployed by the NSA that they called X-Keyscore. And the idea was, of course, mass surveillance. You might have noticed that in the examples so far, the use of strong encryption and the use of strong cryptography more generally would have made things much, much harder. Because if databases were routinely encrypted, if they're somewhere on a server, then stealing them is not as much fun. Of course, you then have to deal with searching on encrypted data. And if websites would routinely require, or two endpoints on the internet would routinely require to see some form of authentication of the other end, then man-in-the-middle attacks again become much more difficult. And of course, some large organizations are aware of this sort of drawback of using strong cryptography. And so interestingly, other things that we learned over the years was that, for instance, a really well-known and respected Swiss company called Crypto AG was in fact part owned by the CIA and the German BND. The company ceased to exist in 2018, by the way, but until then, they sold presumably weak crypto products to third world countries. What we also know is that the NSA has multiple times fiddled around with cryptographic standards, and we know, I would say in pretty certain terms, that one particular standard that governs the creation of random numbers was backdoored by them. And in fact, they're going so far to pay a large American company actual money, traceable money, to include this particularly backdoored random number generator in all of their products. And to top things, we also became aware of the so-called Bull Run program, which was intended to essentially increase the capacity for mass surveillance by really targeting deployed cryptographic schemes. And for a long time, there was a particularly popular scheme out there, in particular for SSL TLS connections, called RC4. But this has now been deprecated. So perhaps we're in a better place here. And in fact, I could go on and on. There are many, many other things that are out there. So we know how weak, in fact, the infrastructure is for wireless telecommunications. So anything that underpins 2G and 3G, this is the SS7 protocol, comes with no cryptography. So it's super easy to get into and to, in fact, do live tracking of users. There's also kind of an inbuilt mechanism in our wireless infrastructure such that your mobile phone will always per default switch to the strongest signal in its vicinity. If that strongest signal comes from a cell phone tower that is in fact compromised and that asks your phone to downgrade from wherever it's operating, presumably 4G these days, to downgrade to 2G where the cryptography was really, really weak, then of course all your over-the-air communication is no longer secure. And we even learned that there are large-scale attempts to introduce backdoors again into our server infrastructure, but it goes further than just what I explained before. In fact, we have learned that certain large organizations in fact intercepted the delivery of server infrastructure from American suppliers, in fact. They kind of en route, they then inserted their own firmware, sometimes even their own little hardware components, packaged them up again and shipped them out. And so really inserted backdoors into the server infrastructure without all of us noticing. It's the same large organizations, by the way, who have been advocating really, really loudly across Europe that we should limit the access of a Chinese manufacturer to the 5G network. And I would say they know what they're talking about because obviously they have been doing this for many, many years now. So can everything be really trivially broken? Well, actually not. And this is also what is in some part behind the contention between the use of strong encryption in real-world systems. So when we all naively talk about the use of encryption, and we, for instance, think about something like a user and a website, or a user and another user, then we think about encryption in terms of these two endpoints. So that, to give you a simple example, if I send an email to a colleague and it's encrypted, then it's the colleague and I who share cryptographic keys, or maybe exchange cryptographic keys, or whatever the details here are. And nobody en route, so obviously the email will traverse the network and hop via multiple computers or servers. Nobody on the route actually has any chance of reading this communication. But this isn't always true. We have to distinguish between what's called end-to-end and point-to-point encryption. Some protocols give you end-to-end encryption. Some protocols only give you point-to-point encryption. So end-to-end encryption means that really the endpoints can only encrypt and decrypt. The routers that are on the route, they cannot decrypt. They cannot look at the data that is being sent around. And that also means from a user perspective that we don't have to trust any element on the route really. If we do point-to-point encryption, then each single point on the route can listen, each point on the route can potentially modify messages, and actually each network element has to be trusted. So in the controversy that is that we have in Europe, but also in the US and in the UK about the use of strong encryption, it's not that the large organizations don't wish users to use strong encryption. They just wish us not to use strong end-to-end encryption. Now, with that, I hope to have motivated you that you should be interested in cryptography and you should be interested in the kind of cryptography that you're using. Now, coming away from this perspective and just then thinking about, also with the examples in mind, how difficult it actually is to deploy strong cryptography in a large system. Because cryptography, in fact, it's a mathematical thing. Encryption schemes, signature schemes, and other things, they live as, in a way, mathematical objects that also have a computer science meaning, so there's an algorithm that implements them. But there's always a gap between theory and practice. And, for some fields, a gap between theory and practice means perhaps losing performance. But for cryptography, a gap often means losing security. And a really important gap in this game is what's relating to the practical implementation of cryptography on actual devices. Because, clearly cryptography is complicated, it's complex maths, there are long keys to be used, and I'm not going to show you a single cryptographic scheme in detail, but I think you should be aware that you never ever do crypto yourself, right? It's always a program, a device, or something like that is executing the cryptography for you. And it has to be like that. Crypto is just too complex. But when a device executes something, it takes power, it emanates electromagnetic radiation, and it takes time to complete. And these factors, in fact, depend on the internals of the device, and the internals of the device are supposed sometimes to be secret. So you've got something that is observable, that is strongly linked to something that is secret. And that's obviously a problem. So by the things that you can observe, you typically can learn something about the secret, and this typically isn't modeled in cryptographic proofs. So what can you see? I already mentioned power, timing, EM. But sometimes systems also give error messages, and they tend to be very, very informative. And sometimes it can happen that a fault occurs during a computation, and it turns out that results of faulty decryptions and faulty signature generations, they can tell us a lot about the secret key that has been used internally. So this additional information can help break otherwise provably secure cryptographic schemes. And this leakage that is available, that has been used by adversaries of all types. Adversaries that just want to break an implementation of crypto because they might want to clone a product. It was very popular for printer cartridges and for pay TV systems. And also some adversaries who want to spy on us or on baddies for whatever purposes. So power analysis has been used by the NSA, for instance, to extract information from BitLocker encrypted devices. So leakage, it really matters, and leakage is kind of complicated to deal with. It reveals information about keys and messages, and it makes certain things that cryptographers really want for their protocols really, really hard, like indistinguishability. And the real problem with leakage is that it goes right to the heart of some of the assumptions that we make for deploying crypto in practice. I mentioned before that nobody is doing crypto themselves, it's always a device. And this is because crypto is hard. But there's a second reason, and this is that for some products and in some applications, there are keys being used that we actually don't want the users to have because they might be able to abuse them. And so some secret keys, they should be really secret to many, many people. And the traditional solution to achieve that in practice has been hardware. There's a good reason why you have got a bank card, and it's not just because you want to have something to insert into a wall or into a terminal, so a physical thing. It's also because there are keys stored on it that really the bank wants to keep secret. So these little hardware things, or secure elements as they're sometimes called as well, they protect crypto keys. And it turns out that this so-called secure hardware isn't that secure after all. And then there were kind of also other solutions developed over time, software solutions like Intel's SGX, ARM's Trust Zone, which were supposed to run programs or parts of programs in some form of secure environment. But it turns out that these environments are also very, very leaky, and they're not nearly as secure as advertised. And again, this is part of the trust anchor for some of the products or for some of the larger schemes. And leakage just basically destroys all of that. So in today's world, if there's a piece of hardware given out, like a bank card, so a credit or debit card or stuff like that, then you can't just sort of claim anymore, okay, well, this will protect your keys. You actually have to prove it via certification. And this is very, very expensive and time consuming. So dealing with leakage, it really matters as well, because there are billions of devices out there, and billions more devices will be out there in the future, and many of them, if not to say all of them, will need some form of protection. And we can't just rely on this idea of secure hardware, because we know this doesn't exist as easily as we hoped it would. And of course, there's also a question of cost associated with products. And for a lot of products, the idea of buying in an externally manufactured secure element is just not really sensible. So really, the challenge that is out there is not just one that is there for people who work in cryptography or cryptographic engineering. It's a challenge where some form of functionality needs to be made available to people who implement cryptography, such that they can produce implementations that are also secure under leakage. And in many situations, this will actually imply that we need to be able to implement cryptographic software securely on sort of small devices. And with small, I mean sort of mid-range processors, 32 bits, with some form of pipelining and hence parallel execution of instructions. Now, the real devil here really lies in the detail, because in order to implement strategies that mitigate leakage to some extent, you often need to make some assumptions about how devices operate on the microarchitectural level. And the reason for that is that because our most successful mitigation strategies, they require that any data that should be secret gets split up into multiple shares, where each share basically looks like a random value, and the leakage of a random value hence is also not particularly informative. But you need to ensure that this kind of shared out stuff remains shared out and independent of each other, and that can only happen if the microarchitecture of a processor plays along and does not inadvertently recombine things, because it's keeping things maybe in registers close by, or there are instructions that kind of get changed in terms of the order in which things are being executed. That could already be induced because of the compiler that realizes that maybe a piece of code can be more efficient if you reorder the low-level instructions. So there's a lot of stuff can go wrong from an engineer writing something in assembly or C, even worse, and what really gets executed on a device. So it's turned out over the last 10 years or so that writing a secure piece of code on a processor of which you don't have the full microarchitectural information is nearly impossible. With that, I come to the third part of the talk, and this is very, very briefly, what is the specific contribution that I make and my group makes? So over the past maybe decade or so, I've kind of been digging in a particular area of leakage resilience, which has something to do with finding out how does a piece of hardware actually leak, so you can then write something securely on it. So we are sort of specialists for developing the statistical techniques that extract the functional form of the leakage of a processor. So we take an actual processor that's on the market, we don't have its full hardware description, we literally just buy it, and then we design leakage experiments that give us lots of useful data. Then we design statistics that enables us to build either proportional or nominal models. So proportional models, they can be used to do sort of certificational attacks. They can also be used for leakage simulators, and nominal models, they are really, their strength is that they explain leakage in the sense that we, for instance, can learn for a specific instruction that executes on a processor architecture what components in the microarchitecture we believe exist and hence contribute to leakage. So this has something to do with reverse engineering as well. We have some ways in which you can sort of do some of these tasks automatically, and we have applied this to a range of mid-range processors, all from the ARM instruction set family, so ranging from an M0 up to an M4. And then we've also kind of developed expertise in further kind of techniques from machine and deep learning that kind of aid this process. Our approach works grey box, and this means that we take any public information that's available, and then we also make certain inferences from this based on having a good understanding of how processor designs really work. Our model building, hence, it does require expertise. It's not sort of completely generic. And we go through several stages depending on also what kind of models we want to build. So for a proportional model, for instance, we look at instructions in isolation. We try and group instructions by using some machine learning techniques in terms of the leakage behavior, I mean. And then we kind of start building models for more complex sequences of instructions. And these sequences, the nature of them depends on the processor architecture. If we build a nominal model, then actually our approach now has been to kind of look at the pipeline stages separately, to look at the memory subsystem separately, to look at other interesting components separately. So we design specific leakage experiments for that, and then we kind of extract a model that explains what contributes to the leakage when we execute a certain instruction sequence. So you might ask, what do you do with that kind of model? Well, so what we've done is we built this model and then we integrate it into an instruction set emulator. These things exist, they're out there, and we just took one that's widely used, integrated these leakage models, integrated some other kind of helpful tools for developers. And then what you can do is basically you write your code either in C or assembly, and you kind of execute it on the device, or you kind of execute it in our tool. And then you can do, certain types of leakage analysis. Again, you could do it on the device or our tool. And what we have found is that the tools that we have, they are really, really good in explaining the leakage of the real devices out there. So, for instance, I've got here two pictures. The top one shows you a leakage detection result when we run a piece of code through our tool. And then the lower one shows you the same leakage detection result when we run this piece of code on the actual device and measure and do the analysis. And essentially, all the instructions that are problematic are identified by our tool. You do not actually have to go to a device and execute it. And this is kind of helpful because a lot of software developers, they don't have a side channel setup, they don't have the expertise to do all the measurements and the analysis. They need some help, they need some tooling. And the quest to produce usable tools has been one of the driving forces for me and my group over the last 10 years, really. And this was also very well appreciated. So this is a project that has been funded by an ERC grant for the last 3 or 4 years now. I want to conclude with some next steps. So we've got two tools called Elmo and Giles, which kind of integrate proportional modeling. We are just working on something that integrates also nominal modeling. There are many more things that perhaps could be done in an automated fashion, and that's quite a challenge as well, a scientific challenge and a mathematical challenge. And we've done an awful lot in this kind of grey box setting on the ARM architecture, but we are moving on to RISC-V together with our partners in Bristol. And we have some first steps for instrumentation of a RISC-V and an idea of how in particular you use the nominal modeling approach in relation to this kind of white box setting that we will be moving to now. With this, I want to conclude. I want to say thank you to you for listening. I also want to say thank you to the ERC for funding this research. And as a link to our website here in Klagenfurt. And of course, none of this, what I've been talking about, would have been possible without my fantastic co-workers and team back in Bristol and now also here in Klagenfurt. So there are many, many names I am indebted to and I was privileged to work with. And with that, I want to end. Thank you very much for listening.